Let's read the question. A potter's wheel is rotating around a vertical axis through its center at a frequency of 1.5 revolutions per second. The wheel can be considered a uniform disc of mass 5 kg and diameter 0.4 meters. The potter then throws a 2.6 kg chunk of clay, approximately shaped as a flat disc of radius 7 centimeters, onto the center of the rotating wheel. What is the frequency of the wheel after the clay sticks to it? Ignore friction. So it seems that this is a problem that has to do with the angular momentum, because angular momentum is conserved when no external forces are acting, and we can see that no external forces are acting on the system of the chunk of clay and the rotating wheel. So then we can start writing net momentum equations, which would mean that the net momentum, angular momentum initial, is equal to the net angular momentum final. So how do we calculate it? To calculate the angular momentum of any object in rotational motion, we can say that that's equal to the L is equal to the I, which represents the rotational inertia, times the angular velocity, or omega, of the object, which means that the initial angular momentum is simply can be replaced as the I, the rotational inertia of the object, times its angular velocity for each of these objects, the potter's wheel and for the chunk of clay. So rotational inertia of the wheel times the angular velocity of the wheel plus the rotational inertia of the clay times the angular velocity of the clay at the beginning should be equal to the sum of the angular momentums of both of these objects afterwards. So that would be the rotational inertia of the wheel times the angular velocity of the wheel final plus the rotational inertia of the clay times the angular velocity of the clay final. Now, one thing we can observe is that it says that the clay sticks to the rotating wheel over here after the clay sticks to it, which means that in the end of the situation, the clay's angular velocity should be equal to the wheel's angular velocity, which means that these two terms are equal. So we can rewrite this side of the equation to be the final angular velocity times the sum of the rotational inertias of both objects. And now we can rewrite this equation to solve for this final angular velocity, because the question asks for the frequency of the wheel after the clay sticks to it. So to resolve this, we divide both sides by this term, which would mean this is our equation to find the angular velocity of the wheel and clay after their collision. So how do we replace all these i's, this rotational inertia of each object? Well, since we know that they're both flat disks, we can find the rotational inertia equation, which will be given on our formula sheet, to be half times the mass of the object times the radius of the object squared. So I'm just going to plug that in for each individual rotational inertia. Okay, one other thing that I failed to point out earlier was the 2 kg chunk of clay mentioned over here. In the question, it states that the potter throws it onto the rotating wheel, which kind of implies that the clay didn't really have any initial angular momentum to begin with until after it stuck to the wheel, which means that whatever this term is really just 0 at the beginning of the equation, which means we can cancel it out over here. And this kind of translates to this section, so that gets cancelled out as well. So let's rewrite this at the bottom. One thing we can observe is that all these terms have 1/2 in them, which means we can multiply both the numerator and denominator by 2 and get rid of this fraction. So that means the final angular velocity of the system is equal to the mass of the wheel times the radius of the wheel squared times the angular velocity of the wheel initial divided by the mass of the wheel times the radius of the wheel squared plus the mass of the clay times the radius of the clay squared. So we can start plugging these things in now. One thing that we can observe is traditionally the angular velocity of the wheel is not represented like this, 1.5 revolutions per second, because revolutions per second is a term used for frequency, which is like cycles per second, while angular velocity is typically written as radians per second. For this question, I think it may be easier to think of it by just kind of moving this initial angular velocity of the wheel to the side. So we'll just kind of move this to its own separate term. Well, now we're multiplying this whole thing by this whole side of the equation by the initial angular velocity of the wheel. So this allows us to, using whatever number we get over here, it becomes a coefficient to what we should multiply by the initial angular velocity of the wheel, which is given by 1.5 revolutions per second. So let's start plugging in numbers. The mass of the wheel is 5 kg. The radius of the wheel is, well, we have the diameter as 0.4 meters, which means the radius of the wheel will be 0.4 divided by 2, or 0.2 meters. So we square that, and divide that by the mass of the wheel, 5 kg, times 0.2 meters squared, plus the mass of the clay, which is 2.6 kg, times the radius of the clay squared. The radius of the clay is 7.0 centimeters, which means that 7 times 10 to the negative 2 meters squared. And we're multiplying all of this by the initial angular velocity, the initial frequency of 1.5 revolutions per second. The question asks for what is the frequency of the wheel after the clay sticks to it, which is why I chose to leave the frequency written as revolutions per second, because we have to solve for frequency in the end, rather than converting this to angular velocity in terms of radians per second, and then converting that back to revolutions per second at the end of the problem. So after plugging all of this into the calculator, 1.41, and so that would be 1.41 revolutions per second, and that would be the frequency of the wheel after the clay sticks to it.